This video is intended to serve as a bit of a primer on how we can use energy transitions based on the quantized energies of systems to determine fundamental features of the system that we're attempting to model. And to that end, I have the energy for the simple quantum harmonic oscillator, the particle in a one-dimensional box, and the particle on a ring. And so what we would need to do when we think about our energy transitions as used in spectroscopy is, what does the selection rule tell us? So the selection rule for the harmonic oscillator says that the delta V must be positive or negative 1. So that means that we could write a delta E for going from, say, V equals 1 to V equals 2. Well, the V plus 1/2 for the final state, which is 2, that gives me 2 plus 1/2. And for the initial state, 1 plus 1/2. Well, the 1/2s are going to cancel. The h bar omega would factor out in both cases. And since these are all evenly spaced, whether it's 2 minus 1 or 200 minus 199, we're going to always end with our delta E being h bar omega. So now, because delta E is h bar omega, the thing that becomes the fundamental feature we worry about is this fundamental vibrational frequency. And so this frequency then is related not only to the reduced mass, but also the force constant in the potential energy from the harmonic oscillator. So we have two masses that are vibrating, and they vibrate out, they vibrate back in, and that vibration is controlled by not only the mass, but the restoring force that brings them back together. That means that if we're using this as a model for a diatomic bond, the two atoms that are in the bond will give us the reduced mass, and the strength of the bond can then be related to this force constant. And so because the fundamental vibrational frequency depends on information that we have about the masses that are vibrating as well as the force connecting them together, i.e. the bond, then this becomes an excellent way to gather some information about the vibrating pair and how exactly they're bonded together. So the next thing we want to think about is energy transitions for a particle in a box. In this case, the selection rule says that it has to be an odd number. So let's just take the first transition, and let's suppose we are doing a transition from state 2 to state 3. Well, all of this will be identical each time, so the only thing we really need to worry about is the difference between the squares of those two states. So we know that these are constants. The mass of what's ever inside that confined area is going to remain the same, and the length of it is also fixed. So if this is the final, then we have 3 squared and 2 squared for the initial. And so in this case, we're looking at 9 minus 4, which is 5. So for this particular transition, we have 5 times h bar squared, pi squared over 2ml squared. Now, this delta E, if we have all of this information, the initial and final state, the length of the confinement, and the mass of the particle that's been confined to that length, then what we're looking at is a prediction for what the energy transition would look like. However, if we don't have all that information, and say for example we needed to find the length and we had the delta E, then what we could do is simply solve for the length, and we know that's going to be a square root. And in this case, we're able to use information gained from doing the spectroscopy, the actual measurement of a delta E, to determine a length. And the thing that we have to be careful about is making sure that we have enough information to be able to properly estimate what two states we're transitioning between. And so with a bit of detective work and a good bit of math, we can use this as a mechanism to determine a fundamental feature of the system, the length of confinement for that particle that's trapped inside that one-dimensional box. So finally, we have the particle in a ring, which is a really good model system for aromatics, because if we want to fill in our levels completely as we go up in the values of K, we have to have, the Huckel number. So let's suppose we're going to go from state 2 to state 3. This would be consistent with the transition rules. So in this case, we're going to go from 2 to 3. Again, we have a lot of constants. Those are going to remain the same. The k squared part is what changes. So we can write h bar squared over 2mr squared. And our final minus initial. And so in this case, we're going to get something that looks very similar to what we had here, because in both cases we have squares. And so our delta E then is 5 times h bar squared over 2mr squared. Now, for a particle on a ring, because we're typically talking about hydrocarbons, they're not going to be perfectly circular. However, this becomes a really good estimate, and if we have all of this information, then we can predict a delta E for the HOMO-LUMO gap for our aromatic system. However, if we have the delta E and we wanted to come up with an estimate here, we do the same thing that we did with the length of the one-dimensional box. We can solve for R. And so in this case, once again, we'll have a square root. And in this case, the fundamental feature of the system that we're looking at is the effective radius. If we have the effective radius, then we will be able to recognize that different aromatics will have a different number of bonds in that circular pi system, at which point we know that the size of the molecule will be different overall, and this is a way of using the spectroscopic idea that our delta E's are going to have specific values tied to something about the system. And so in each case, whether it's the harmonic oscillator for the fundamental vibrational frequency, the particle in a box where the length helps us determine what the spacing of levels will look like, or the particle in the ring where the effective radius helps us determine what the spacing of these look like, we're using the same idea, that spectroscopy reveals to us something about the fundamental structure of the systems we're using the quantum mechanics to model.